Hello, good afternoon. Welcome back after the Easter holiday and the reading week. Since we haven't been format for about 2 weeks, so let's have a brief review of what we have taught before the holidays, and then we will continue with our discussion on fruits, and then today we will also start in, the discussion of a new chapter on oscillation. Now let's check the PowerPoint. Now, do you remember what is meant by the Boulougner's equation? Now, we proved by the conservation of energy, if we follow a streamline, then we have proven that by the conservation of mechanical energy, that's along the streamline, this quantity is going to conserve. Now, this quantity consists of three terms. The first term is the pressure, okay, is a pressure. The second term is essentially the potential energy. If you multiply the factor of rho, the rho is density. If you multiply by a small volume v, that becomes the mass, right? So mg, the mass mgh is the potential energy, is that right? So it is the potential energy, actually it's the potential energy per unit volume. And this term, if you multiply again a small volume delta V, the rho V become m is half mv squared. So it's the kinetic energy. So this term is essentially the kinetic energy, but per unit volume. Since you are talking about the density now, so you're talking about per unit volume. So these two terms are actually the mechanical energy, and this term, the pressure P, is actually corresponding to the work done by the external pressure. Okay, so the equation itself actually reflects the energy is conserved along the streamline. Okay, so this is an expression for conservation of energy. So when you follow a streamline, this combination is going to be a constant. Individual term may change. For example, the velocity may change, the heights of the flow may change, and also the pressure may change, but this combination is going to be constant. Okay. We have discussed about this example using the Boulougner's equation, applying it to a so-called pitot tube for measuring the speed of an aeroplane with respect to the still air. Okay, so we have already discussed about it. We are not going to repeat it. Now, but there's an important application of the Boulougner's principle is on airplane lift. Okay, now strictly speaking, Boulougner's principle is not very accurate in obtaining the lift force, but it is qualitatively correct. Okay, now if you want to have a very precise treatment, you have to take in also the account of the viscosity of air, and also you have to take into account all those turbulence effects. Those effects are actually important. But as a simplified model, we assume an ideal fluid flow with no viscosity, and we obtain a qualitatively correct description for the lift force on an airplane. Okay, so this is a cross section of the wings of the airplane, and you can see that in our previous discussion, we have seen that this cross-sectional shape is not symmetrical with respect to the upper side and the lower side. And when air passes through, you see that the velocity at the upper side is higher than the velocity at the lower side. And by the Boulougner's principle, this two term, the height is essentially negligible because the difference in height is so small, so we neglect it. So this two term, P plus half rho V squared, is going to be constant. Okay, so if V is small below the wings, then the pressure will be large. And if V is large above the wings, then the pressure P will become smaller. So that will be a difference in pressure. The pressure below is larger than the pressure at the top. So that will be a net force that lifts the airplane wing. Okay, so this is the origin of the lift force. Now, this is quantitatively not going to be accurate because we ignore all those complicated factors. But qualitatively, it successfully described why there's a lift acting on the airplane wings. Okay, we have seen this before. I don't repeat it. And experimentally, we find that if we put the pressure difference between the upper and the lower part of the wing on one side, and we put all the kinetic energy term which involve the half rho v square on the other side, we find that this combination v1 square plus v2 square, different in the square of the speed between the lower and the upper surface of the wings, can be written as a constant CL, which is known as the coefficient of lift, multiplied by the square of the velocity when the air is very far away. So this is an experimental fact, but it holds for quite a wide range of frequency, wide range of velocity. Okay. Now the important ideas that follow is that if we write the difference in the square of the velocity in this way, we can write the lift force like this. It's just like it's very similar to the drag force you encounter in chapter 5. In chapter 5, we have learned about the air resistance, right? The air resistance is proportional to half the coefficient of drag rho a v square. Okay. Now we have another very similar expression, but for the lift force. For the lift force is equal to half rho a CL. CL is another coefficient called the coefficient of lift, v square. And A now refers to the area of the wings. Okay, the area of the wings, but not the frontal cross-sectional area anymore. Okay, now so the expression is very similar actually. And we have already explained to you how we can increase the coefficient of lift. The coefficient of lift actually depends on the angle of attack, the angle that the wings mix with the incoming air, and also the cross-sectional area of the wings. So if we want to increase the lift coefficient, so the lift force will become larger, we can either change the angle of attack. We can use a larger angle of attack, and we also can for the passenger plane, we can also lower the wing flap. So that's the shape of the wings is changed, and the lift coefficient will become larger. Now this is especially important when we are taking off, when the plane is taking off, the velocity is not that high. And so we have to create extra lift. And the method to create that extra lift is to vary the lift coefficient. Because the velocity is not that high, so we need a lift force that is at least equal to the weight of the airplane, right? In order to lift it up. So we increase the coefficient of lift when the plane takes off. So that will make it easier for the takeoff. Okay. Now we have discussed it before. We don't repeat it. Now you may wonder why there is a tail wing in a passenger airplane. Now this is the model of a passenger airplane, right? This is the main wing, but at the back or at the rear side of the airplane, you have the tail wing, a small wing at the rear end, right? So what is the function of that? Now it happens that because the lift force actually is acting on the wing, right? Because it's the air that produces the pressure on the wing. So the center of lift of that force, which is called the center of lift, lie at this position. It is the position where the lift force acts on the plane. It is at the position of the wing. Okay, so you imagine you have this point that represent the line of actions of the lift force. So this force is upward, but it happens that this is a design. It happens that the center of mass of a passenger plane is usually a little bit in front of the center of lift. So the center of mass is actually in front of the center of lift. So the center of mass is here, but the force of the gravity is downward, right? It's acting downward. The lift force is acting upwards, but the weights of the airplane is acting downwards. So the two forces are not coincide each other. the center of gravity is actually slightly in front of the center of lift. So the two forces, one up and one down, one upwards and one downwards, they could produce a torque. And that torque will tend to turn the aeroplane with its nose facing downward. And the plane will crash if you don't control that, right? Because the moment is turning it anti-clockwise, right? So the anti-clockwise motion will make the nose of the airplane to go down, and that will be a crash if you don't control that tendency. Now, how do people prevent that to happen? Is by the tail lift. Okay, when you have a tail lift here, when it passes through the air, is the tail lift actually the tail wing actually produces a lift that is downward, and I call this downward force T. Now you see this lift, although the force is not that large because the wing is actually small, but it is at a large distance from the center of mass. Okay. Now, so if I take moment about the center of mass, then in order to balance the two moments, okay, the lift force multiplied by the distance between the center of lift from the center of gravity, I call it dl, must be equal to the tail lift T multiplied by the distance of this point of application from the center of mass, which I call dt. So that maintains the balance of the airplane. So the plane will not turn up and turn down. Now, because this is easier, some people ask me why these 2 points is not the same. The answer is that we can adjust the angle of attack of the tail lift, of the tail wing, to control this force. And it would be easier for us to maintain the equilibrium. You have a range to control. If you make the center of mass to be exactly at the center of lift, then you have no method to control the equilibrium. If, for example, suddenly the people go to one side of the airplane and the center of mass shift forward, then there will be a tendency of going down, and you cannot control it. But with the tail lift, and there's a slight difference between the two center, you can actually precisely control the tail force, the tail lift force, to maintain the balance. That's how you maintain the balance of the airplane. Now, when the plane is taking off, now you probably have noticed that when the plane is taking off, the plane actually is not horizontal. Have you seen an airplane taking off? The plane does not take off horizontally, but it takes off at an angle. The wings actually makes an angle with the horizontal. Then that is the angle of attack. So in order to take off, the airplane actually tilt itself at an angle. But how to produce the tilting force? How to produce that moment is by increasing the tail lift. The wings will flip upwards, and so it will induce a larger tail lift downwards. And because of the moment is clockwise moment, so you tilt the heads, the nose of the airplane upwards. And that's how you control it. Okay, that's the idea. Now let's see for I have a video for you. That video is sorry for the video is in Cantonese, but I hope you understand the basic features.
願我會揸火箭帶你到天空去，在太空中兩人住。
活到1000歲都一般心醉，有你在身邊多樂趣。 哇，博士又有紙飛機又唱情歌咁，究竟係做啲咩實驗咁浪漫啊？
我今日嘅實驗咧，就係教大家接紙飛機，睇下邊一隻飛得最遠。呢個同流體力學咧好有關係嘅。
好唔浪漫咯！
嗱，呢一度咧有好多種唔同嘅紙飛機，有啲咧就好尖喎，同埋咧個翼窄啲嘅；有啲飛機咧個翼咧就闊好多啦，但係咧就掘頭喎。呢兩隻都係啦。有啲飛機咧，哇個翼咧翹嚟翹去嘅。咁一陣間我哋就會試下掟下睇下邊隻掟得遠啲同快啲咯。
好啦，陪你玩下啦。博士啊，咁我哋試飛邊一隻飛機先啊？
嗱，呢隻啦，最傳統嘅尖頭飛機，好容易整嘅咋。
好，試下先。
哇，都幾遠喎！
係啊，同埋佢係一支箭就飛咗出去。
好快啊！
係啊。
誒，我哋試下呢個啊！嗱，呢個翼咧就闊啲啦。
哦。
同埋掘頭嘅呢個。
又會點樣咧？哇！佢好似有啲向上升。
有少少向上升，其實你再細力啲，可能咧就會再順啲。
我要再細力啲啊！
係啦，呢隻你試埋啦，不如。
哇！呢隻好奇怪啊！
呢隻古靈精怪啦，呢隻叫做。
試下先。
哦，跌咗咯！
博士啊，點解唔同嘅飛機接法咧，會令到佢飛嘅方式咁唔同嘅？
嗱，我哋逐隻講啦。嗱，呢一隻咧就比較傳統嘅，咁個特色咧就係個翼咧比較窄啦，咁但係咧好尖嘅喎。咁如果你接得好嘅時候咧，呢度好密嘅時候咧，咁就變咗咧，其實佢迎風嘅嗰個面積咧，呢度面積係好細嘅。咁即係話咧，佢受到空氣阻力影響好少，所以你見到佢頭先係飛得好快。但係因為佢嘅翼窄咧，所以空氣俾佢嘅升力咧會少啲嘅，所以咧就喺空氣裏邊唔係好停留得耐啦，佢就會好快咧都跌落去啦。嗱，呢一隻咧就好啲啦。如果你想飛長啲嘅話咧，佢翼闊喎，咁我於是咧空氣俾佢嘅升力咧就強好多，咁所以咧佢就可以飛得遠啲，但係佢就冇飛得咁快啦。同埋咧，佢係個機頭咧係接咗入去後邊嘅，所以個重心嘅位置咧就向咗後邊。咁呢兩個因素咧，亦都會令到佢咧喺空氣裏邊咧，其實會飄上飄落啊咁樣啦，會飛得比較長久一啲㗎。
係，不過見到佢係會咁樣升下又跌下，升下又跌下，即係嗰啲空氣一路承托住佢咯喎。係
啊，當佢快嘅時候咧，其實咧嗰個升力嘅中心改變咗啦，令到佢咧真係有時會升翻上去嘅個機頭。係啦，咁咧呢一隻咧就個表現最差啦，係咪？咁啊，因為佢太多古怪嘢啦，機翼又細啦，個升力又低啦，咁所以好易跌咯。咁啊，仲有另一個問題喎，就係咧，其實佢前面呢度咧有兩塊嘢咧係接咗上去嘅。咁嘅時候，你可想象下佢撞個空氣嘅時候，個面積咧就大啦，迎風面積大，受到空氣阻力影響好大啦，所以咧佢飛得冇幾耐嘅時候咧，就噥一聲咁跌咗落去咯。我哋隻飛機咧好得意嘅，佢會轉圈㗎。
轉圈？
睇住到喎！
哇，點解架飛機咧識得翻轉頭嘅？
嗱，我哋睇下呢隻迴旋飛機嘅結構先啦。你見到咧，佢嘅機翼咧唔係完全平嘅，有少少向上拱嘅弧度㗎。咁其實咧呢一樣嘢係可以咧提高個升力啦，令到佢承托得更加好嘅。咁另外一樣嘢咧就係佢嘅機尾啦，呢個就係旋轉嘅秘密。見唔見到個機尾個尾翼咧唔係平㗎，而係向上咁樣斜咗上去嘅。咁當喺氣流嗰度衝前嘅時候咧，呢個向上斜嘅斜度咧就會令到隻機尾翼咧產生個向下嘅壓力，令到個機尾向下，咁個機頭咪向上咯。於是咧佢就會產生一個旋轉，做一個大回環㗎啦。
原來係咁，咁其實流體力學都有佢嘅浪漫之處啊！不如你快啲教我整一隻可以飛到好遠嘅飛機啊！
Okay, now the idea is you notice the tail wing, okay? You see the airplane that can fly 360 degrees is because of the tail wing. The tail wing is flipped upwards. So there will be a downward force when it passes through air. There will be a downward force at the tail wing. And that downward thrust is actually produce a moment that tilt the airplane with its nose facing upward. And so that's why it goes upward like this. Okay, and there's a trick of controlling the so-called elevation of the airplane, the nose rising up or lowering it down. Okay. Now let's go back to the last slide about now this is a problem of applying the Balloonian principle to a tank that is leaking. Okay. Now, suppose we have a tank. For simplicity, we assume it to have a uniform cross-sectional area A. And initially, there's a height of water H inside the tank. So the height of the water level is as a height H above the base of the tank. And there's a small hole of area A naught at the base of the tank. So water is leaking out. Okay, so water is leaking out from the tank. Now let's draw a streamline. The streamline extends from the top of the water level all the way to the water outlet, to the hole. Okay, so there's a streamline here. And we apply the Bernoulli's principle along that streamline to describe the water leaking out of the tank. Now, so first we look at the top of the water level. Okay, now because this side the top level of water is exposed to air. So the pressure is essentially the atmospheric pressure, and we denote it by P naught. We make the reference point of the potential energy to be at the base of the tank. So the potential energy at the base is called zero. And the potential energy at the top of the water level will be equal to rho GH. Okay, H is the height above the base because we make the base to be the reference level. Okay. So there's a term rho GH, and because the cross-sectional area is so large compared with the hole, okay, so the water level is decreasing quite slowly. Okay, so the speed at the top is very small compared with the speed of water leaking out. So that's why we can actually neglect the speed at the top, because the cross-sectional area is so large. So the water level is decreasing at a very slow rate. So we can neglect the half rho v squared term at the top. Okay. Now, how about on this side, at the outlet? Okay, at the hole, the pressure is atmospheric pressure. Why? Because when the water leaks out, it is exposed to air, right? Nothing else is exerting pressure on it except air, right? So the pressure is actually atmospheric pressure. The pressure is actually the same as the top of the water level. So both of them are being acted by the atmospheric pressure. The height is of course zero, right? And we have a large velocity here. So we have this term half rho v squared, where v is the exit speed, the speed of water coming out from the hole. Okay. Now, so this equation is easy to solve because P naught cancel on both sides. So rearranging term after canceling the rho, we get V equal to square root 2GH. Now, this is very familiar actually. If you have a body, if you have a ball dropped through a vertical height of h, okay, you release the ball at the vertical height of h, then the velocity at the bottom point is equal to square root rho GH. This is simply the conservation of energy. Now you are applying the conservation of energy not to a ball falling down, but to a liquid. The liquid loses the potential energy, and it becomes the kinetic energy of the liquid when coming out from the hole. Okay. Now, how can we calculate the rate at which the tank is being empty? Now, the change in volume dV dt. I don't know if you remember this equation. How to calculate the change in volume, the rate of change of volume? Now, it's easy. For the water level in the tank, if you multiply the cross-sectional area by the heights, you got the total volume. Is that right? The total volume of water inside the tank. If you differentiate, the differentiation goes to the cross-sectional area is unchanged, so the differentiation goes to the height, so it becomes the HDT. And these two terms multiplying together will give you the rate of volume change. Okay, the rate of volume change. Okay. And the volume is now decreasing, right? The volume of water inside is decreasing. So H is also decreasing. So the sign is correct, also correct here. But if I equate this volume change to the amount of water leaking out per unit time, then I have to multiply the area of the hole A naught with the exit velocity. A naught V is the volume of water leaking out. But since this quantity is positive and dV dt is negative, I have to add a minus sign here. Okay, the minus sign is simply to make the equation correct in terms of the sign. Okay. Now I don't know if you remember why A naught V is the volume rate of flow. You probably have forgot the equation of continuity. Do you remember this derivation? We calculate the dV dt through a surface, right? And we find that it's equal to VA, the velocity multiplied by cross-section area. So the velocity multiplied by the cross-section area always give you the rate of change of volume, okay? Or the amount of, or the volume of water, volume of fluid flowing through a given surface per unit time, okay? Now, so we are going to solve this equation because we know V, right? So we can solve this equation or we express this equation in terms of H, and we can solve the equation. So this is the resulting equation. And V is expressed in terms of H. So it's become a constant multiplied by square root H. Okay. Now we can rearrange the term. We move the square root H to the left-hand side, and it becomes 1 over square root H. And we move the dt to the right-hand side, and we integrate both sides. Okay. Now the starting time is 0, and I assume initially the water level has a height of h naught. So this is the initial water level h naught. When at the time t, the water level has decreased to a height of h. So h stands for the height of water at the general time t. So the upper limit become h, and on the right-hand side become t. Okay. Now the integration is easy. It gives you 2 square root h, evaluate h minus h and h naught. The right-hand side simply gives you a t, right? So I rearranged this. I evaluate the square root h at upper and lower limit. I got this term. I moved the 2 to the right-hand side. I got this. And if I want to find the time to empty the tank, emptying the tank means all the water has leaked out, right? So h eventually will be 0, meaning all the water leaks out. So if I put h equal to 0 here, I got the time for the tank to empty itself. And this is given by this. Okay, so this is a very simple derivation. Any problem here? Now, I'm not going to talk about volticity because this is a difficult question. It depends on the viscosity of air. And volticity is just the vortex is actually a very complicated phenomenon. So I'm not going to teach you about the details. But I want to show you some of its features, which is very interesting. Just to let you have a brief idea. You may have heard about a toy called so-called air cannon, or there's a technical term for it, air soaker. Okay, this is a band name actually, as band name. Now the toy is like this. You have a rubber band at the back. So when you put and release, the rubber band will push the air inside the air cannon out of a small opening. So this opening is small in diameter. So when the air comes out, it goes from a area of large area to an area of a small area. So the air will increase in speed. So it will speed up when coming out because the area of the exit is so small. So as a result, there will be the air at the center has a higher velocity, and the air velocity close to the rim of the opening will be slower. So there will be a difference in velocity between the two layers. And as a result, because of the frictional force or the so-called viscosity between the two layers of air, that will form a vortex. So the vortex will form like this. Okay, because the air at the center has a high velocity, and the air at the rim is at a low lower velocity. So the friction between the two layers will cause a vortex to form, and this is essentially of this shape. So the vortex will become very stable, and it will extend travel a long distance before dying down, and that creates a very interesting phenomena of a vortex coming up. This is the typical vortex. If you put some smoke inside, you will see a very interesting vortex traveling a long distance. Now, why the vortex form? This is a schematic illustration, it's not a real thing, but it helps you understand why the vortex form. If air does not have viscosity, then the red molecule coming out from the air cannon, it simply dissipates the surrounding molecule. It simply dissipates those molecules away from it. But it does not create when circulation, any vortex. Okay, but with viscosity, things becomes different. When the red molecule comes out, there is friction between adjacent layer of air, and that frictional force will induce a turning effect, will induce a torque, and that result in a vortex. Okay, so that is a very intuitive understanding of why vortex form due to viscosity. And vortex is actually very important for airplane flight. You see, as we say, when the airplane wing intercept the incoming air, the airspeed at the top of the plane is higher than the airspeed at below the plane, because below the wing, right? So the velocity at the top is higher than the velocity at the bottom. So essentially, if you think about the angular momentum do not conserve, because there will be a vortex like this. Essentially, the upper air velocity has a higher velocity than the lower air velocity. So there will be a net rotation like this to happen. So the angular momentum does not conserve. Now the point for the angular momentum to conserve is that after the downwash of air, there will be a vortex forming in the opposite direction. And that tends to conserve the overall angular momentum of air. Okay, and of course that is due to viscosity again. So viscosity is actually a very important phenomenon in physics, but we don't have time to discuss about it. I show you a Hoxiao-Fei. The Hoxiao-Fei is about the air cannon. I think some of you might have seen it before. I have an extract for that.
喂，你都幾勁喎打機。係啦，使乜講？你要逼我啊！我要出波動拳。你有冇啊你？我深藏不露啊！
對住裙底。
喂，錯幾都錯唔到波出嚟嘅？我咪係咯，咁大隻都出唔到波，搞錯啊！唉，唔玩啦！搞錯啊！咁渣嘅你。
唔係大隻咗，係你咗。
錯極都錯唔到波出嚟。
出大唔識，出大冇呢招。
唔識咪學咯，蠢到死。
大叔，你邊位啊？
我係阿龍，
邊位阿龍啊？
教你戳波動拳嘅龍，你兩個跟我嚟啦！
師傅，
教我哋波動拳。
呢幾個資質太差，我要用啲道具先得。
道具，你道具。
咩嚟㗎？求其揾個爛膠土加張用過嘅保鮮紙咁款嘅？
波動拳。
哇！好犀利喎，但係我 乜都睇唔到喎，係咪大風咋？
睇唔到啊！
梗係唔係啦？俾啲煙落去，你就可以睇到好清楚㗎啦。
哦，
波動拳，
哇！睇到啦，今次
見到啦啩？
阿盧師傅，點解你個波動拳咁勁嘅㗎？
就因為咁樣嘅，其實咧個波動拳咧個桶嚟嘅啫嘛。嗱，不過咧佢後邊咧見唔見一個好大嘅膜啊？咁咧仲有條幾條橡筋喎。當我拉去後邊嘅時候咧，其實條橡筋咧有個好強嘅力，將塊膜彈翻轉頭。好啦，塊膜面積好大嘅喎，一彈翻轉頭嘅時候，係咪將個桶裏邊嘅空氣咧推出嚟啊？
哦，係啊，係啊。
但係咧塊膜係大啦，但係咧個出口咧就好細喎。你有一個大面積嘅地方，將啲空氣推出一個細面積嘅地方，嗰啲空氣咪會加速咯。有啲似咩咧？有啲似針筒啊！一撳咧，針筒口嗰度咧好尖嘅喎，咁嗰啲水咪咇一聲咁出嚟咯。所以咧就會將啲空氣加速到好快，嘣一聲打到好遠咯。
好犀利啊，師傅！好想學啊！
嗱，為咗訓練你兩個咧，我已經準備咗2個頭盔，你哋戴咗佢之後咧就可以互射噶啦。你唔係咁戴㗎。
我今次對你
嘛。
比試好簡單，我同 Regina 咧會喺頭盔上面擺隻杯，然後鬥快用空氣炮射跌對方個杯啊 ！Regina 接招啦 ！Round 1 start！
你可唔可以？
慢鏡睇一次，係 Regina 個杯跌先㗎，哈哈哈哈！
暗仔啊，要報仇 ！Round 2 start。你可唔可以射準啲㗎？冇力㗎！哇！我想問下你練緊啲乜嘢咧？你個視線咧其實冇咁高㗎喎，我想問下。
佢有呢個瞄準㗎，我冇。
你有啊？
你有啊？賴地硬，你睇下，呢個比賽唔公平，我再嚟過。
有咩唔公平啊？呢啲俾你訓練下啦啫嘛。
但啱啱咧，我射都射唔中喎。
其實咧，你見到個出口好窄噶嘛，咁所以咧嗰個炮咧，其實個風咧係好集中喺呢個位置嘅。咁你眼界唔好，咁咪驗下眼啦，咁咪射得唔準咯。
緊要去睇下可以升啦。哎呀，唔係喎，但係咧佢哋呢啲咧只係俾啲小學雞玩嘅啫嘛，最多唔係吹低嗰啲紙杯。
喺呢個時候，我怕我都要鬆我支大炮出嚟啦。條腰帶鬆咗啫，其實喺嗰邊。
哇！
呢支巨型空氣炮睇落真係好架勢，係咪大啲威力就會勁啲？等我揾啲紙箱去試下先。
我知係大唔大先。大。嗱，咁要你幫下手喎，你咧就固定佢。嗱，我哋咧就負責打冧前面啲箱。
大隻。
哦。
3、2、1 ，Go！
哇！只係用一炮，7米以外嘅紙箱就應聲倒地，好勁啊！嗱，慢鏡睇睇，煙圈成個波動拳咁款，啲紙箱一掂到個煙圈就頂唔住，冧晒啦！
喂，不過阿龍咧，我想問下，點解咧個體積大啲，威力差咁遠嘅？
嗱，你就講咗個重點出嚟，個重點就係體積夠大。走咯。嗱，咁個體積夠大係咩咧？裏邊空氣多咯喎。其實咧，對一樣嘢嘅衝擊力咧，用咩嚟量度咧？要用動量嚟量度嘅。咁動量第一樣嘢，個空氣個質量咧要夠大。第二咧，個速度要夠高。如果個質量又大，速度又高嘅時候咧，咁個衝擊力咧就夠強噶啦。咁其實咧，呢一支炮咧就勝在裏邊夠多空氣，而且一個膜咧個面積好大，一推出去嘅時候都好快嘅，咁嘣一聲咁咪冧咗咯。
你塊面嘅面積你推出去啊，一推出去就會冧噶啦。OK，Go！
唔好玩住先啦，喂，有啲正嘢俾你哋。喂，我有啲形狀俾你揀喎，三角形啦，有正方形啦，喂，心心女真係最中意噶啦，唉，
我都冇得揀嘅，呢啲咁嘅形狀有咩用啊？
嗱，咁可以俾你感受下咧，要俾唔同形狀嘅煙圈射到咧，會有咩感覺咯？
哦，
你先啊，你先啊！
點解係我啊？
好，俾你感受下三角形煙圈嘅威力嚟咯。
3、2、1，哇！咦，點解係圓形嘅？
我哋之後分別試咗心形、正方形同星形，發現所有射出嚟嘅煙圈最後都變做圓形㗎。 點解嘅？係咪個大炮知道咧圓形先包得住你啊？
你傻嘅咩？你哋試嘅時候都係咁啦。
但係點解我哋頭先用任何嘅形狀噴出嚟都係圓圈嘅？
嗱，不如我解釋下點解會有煙圈先啦。嗱，當啲空氣喺個窿嗰度衝出嚟嘅時候咧，其實速度好高嘅。咁而周圍啲空氣咧，其實速度咧就好慢嘅，差唔多唔喐嘅。咁於是咧，出邊啲空氣咧就會兜一個圈，走翻去後邊填補翻個空隙噶咯喎。但係原來空氣咧有摩擦力嘅，當啲空氣走翻轉頭填補個煙圈嘅時候咧，其實就會產生一個旋轉啦，因為摩擦力嘅緣故咧，兩邊嘅空氣就會有旋轉噶啦。而呢個煙圈咧有一個穩定性，佢可以喺空氣上邊咧向前一路移動，好一個好遠嘅時間嘅。嗱，頭先你見到正方形出嚟嘅時候，嗰個煙圈係點㗎？佢出嚟嘅時候好似有啲形狀似翻個正方形嘅，因為咧喺呢個咁嘅出口嗰度嘅時候咧，其實佢哋嗰個氣壓咧同埋個速度咧喺唔同嘅地方都係唔均勻嘅。咁所以啲空氣彈到出去嘅時候咧，啲唔均勻嘅氣壓咧就會產生個震動。咁呢個震動咧就會慢慢咁將個正方形咧變形啦。咁後來咧，當啲震動慢慢減退嘅時候，個正方形咧就慢慢變成一個圓形，最後個圓形圈圈吹吹啦。
哦，
哇！不過要咁大支嘢嚟學波動拳都幾麻煩。
唔緊要啦，你屋企夠大啊，擺喺你屋企學咯。
打男朋友打男朋友。
大隻贏咗。
Okay, let's take a break for 10 minutes, and after the break, we talk about oscillation.